Okay, so welcome everyone to the second Chandrasekhar lecture. So Professor Tadashi Takayanagi is going to continue the wonderful lecture he gave yesterday, and today he'll tell us about gravity duals of CFTs on manifolds with boundaries.
Thank you very much. I'd like to also thank again for this wonderful opportunity to giving a lecture here. So in my second lecture is about this something called end of the world brain in the context of holography, and also its duality to conformal field theory with boundary. So I'm going to talk about both quantum field theory aspect and also holographic aspect where we have some non-trivial boundaries. So let me start. So this big picture is like what we are going to talk about, very simple. So we have a baroque spacetime where, for example, we are living here and the gravitational waves coming, but there is a very strict wall, rigid wall here. This is what we call end of the world brain. And the gravity wave, for example, comes completely reflected back. So this is a boundary of space-time. But this is a very simple object, but this quite recently plays a very important role in the context of holography and its connection to quantum field theory. And this is sort of D-branes in string theory. D-branes in string theory plays a very important role in a context of many string dualities and also some application to many different setups. But so this end of the world brain is a kind of brains in a gravitational space-time, but this also crucial rules as in holography. The reason is like this. This is a very rough picture. So we have a gravity and the end of the world brain. This is the real end of the space-time here. But in the holography, you usually have another boundary. So usually ADS-CFT, for example, says this Untitled Chapter space here, and it's equivalent to some quantum field theory, lives on conformal field theory, lives on the boundary. But we add extra one more brain. This brain is different from this boundary. This also leads to some boundary, but this is, as I will explain, so this is a dynamical brain. We can fluctuate metric here. In other words, we impose Neumann boundary condition. And the usual ADS-CFT, we impose Dirichlet boundary condition for the boundary where CFT lives. So this is the Dirichlet brain, and this is a kind of Neumann brain. But anyway, in this setup, so gravity is defined here, and there is a dynamical brain, and the gravity dual of this setup, so CFT dual is given by CFT lives on some manifold, but with non-trivial boundary here. So this is a main framework which we are going to work with. So this is and in special case where this boundary condition is very, very nice, so that it preserves some part of conformal symmetry. This is called boundary conformal field theory. I write it BCFT. I will explain this later more. But this kind of end of the world brain appears in many applications in the context of holography. So this is first of all, this gives a gravity dual of boundary conformal field theory. So there are CFT and some boundary. And in special case, it's called BCFT. There is a boundary which is preserved conformal symmetry, this is BCFT. But you can generalize to the case where boundary don't preserve scale invariance and conformal symmetry, and still we can use this kind of holographic setup. I will explain. And also this plays a very important role also these days about in the context of black hole information problem. I'm not going to detail, but I just briefly mention in some part of my talk, but this is not the main point of this talk. But so in the context of Randall-Sunderland or brain world or Cauchy-Randall setup, there is this kind of end of the world brain plays a very important role because there is a dynamical gravity localized on here. So we have some gravity duality between gravitation, classical gravity, Untitled Chapter space to some quantum gravity on the brain. And finally, also this is also related to my talk in the end. So this setup can be useful to understand non-equilibrium physics, especially in the context of a process called quantum quenches. So this is first proposed by Calabrese and Caddy, and this is a very nice formulation in terms of boundary states. So we have we take a 90-degree rotation. This is a space time-like boundary, but we can have a space-like boundary, just 90 rotation. And this part we treat it as a Euclidean time formalism. So then this looks like this is given by something called boundary state or Caddy states, and that time evolution of Caddy state actually gives some very basic example of the non-equilibrium dynamics, thermalization by time evolution. This describes quantum quench process. And its gravity dual is given by Hartmann-Madsen, and this is exactly using this end of the world brain. And I will explain. And we basically going to also generalize that framework and then what we can see. So my first part of my talk is related to this one, and the final part is related to this. So here is a reference. So
Excuse me.
Yes.
What is the motivation behind using a D-brain at boundary?
Sorry, motivation to use what boundary?
D-brain as a boundary.
This is not the D-brain. Maybe you can think as Orient fault in string theory because it really terminates the space-time. Is that okay? I'll come back to that later. But in D-brain, so we can have some kind of defect inside. Then it's much like D-brains. In string theory, everything is like D-brain. But here, really space-time end here, it's more like Orient fault. Okay. Yeah, so if any questions, please just terminate anytime. And so this first part of my talk, maybe this is a more main part, is based on this collaboration with Jonathan Harper, who is sitting here, and also Hiroki Kanda and Kenya Sutaski. They are our graduate student. Jonathan is our postdoc. And this is about derivation of G theorem from very simple proof of G theorem from strong relativity. And also we will discuss its holographic interpretation. Then this end of the world brain plays very important role. This is my first part. And second part, if I have time, I want to also talk about explicit example of this, non-trivial dynamics of end of the world brain. Namely, we put some localized scalar on top of end of the world brain, and we can see some renormalization group flow, also interesting phenomena, which is called it's an entanglement phase transition. This is a work with Kanda and Sakamoto and Sato and Suzuki and Tasuki. They are our graduate students, and Kawamoto will join, I think, in this workshop later. And Jisha, who is a former student, he's in postdoc in Harvard now. Okay, so let me start. So this, the contents of my talk is like this. I will give some introduction first, and already I explained. And then I go to overview of this holography with end over the world brain, which is we call it ADS BCFT because it's dual to boundary conformal theory BCFT, and then go to G theorem. I would like to give some how we can derive this G theorem in an entropic way, and then go to holographic interpretation, and also rest of the time I want to talk about end over the world brain dynamics with some localized scalar fields. Then we can see many interesting applications. Okay, so here is a sketch of ADS, which I will go into details later. But of course, we know this ADS safety. So this ADS safety claims that bulk and gravity on anti-Doshita space in D+1 dimension is equivalent to conformal field theory, which lives on the boundary on flats. In this Poincare metric, it's like flat space. But in the if we put some at this end of the world brain I mentioned, so then this is one typical setup. We can put anywhere, which follows some, which as long as it satisfies nice boundary condition. And okay, there is. Okay. Sorry, I'm not the right person to answer. And yeah, so we put some end of the world brain. For example, this red thick surface. Yeah. And it surrounds some region. And then it ends on some boundary. So this region we are interested in. So conformal field theory lives on this manifold M with boundary here. And we extend this boundary towards the bulk like this. And then how we can determine this surface, I will come back later. But basically we impose Neumann boundary condition. And the region inside is gravity dual of this conformal field theory on BCFT on M is dual to gravity on this manifold N with boundary. So this end of the boundary. So and the end of the boundary fluctuates, so that corresponds to boundary dynamics. So this is a rough sketch. Yes.
How do you determine
end of the boundary? Yeah, I'll explain. Yes, thank you very much. Yeah, that's a really important. But indeed, this is how we derive that boundary condition. And we have some. Yes.
Is the physical interpretation of the end of the world brain in the bulk that you have a gap theory or?
End of the bulk. You mean gap in the bulk or?
Yeah.
So, it is a conformal invariance. We assume this bulk M is a conformal invariance. And boundary can also support conformal invariance. But also you can break boundary conformal.
I see.
Both are possible.
I see. But the fact that in the bulk you are terminating ADS,
Yes, yes, yes.
At in the bulk also ADS ends, right?
Yes, yes, exactly, exactly.
So doesn't that mean that you don't have a conformally invariant theory anymore?
Yeah, but this boundary also looks like lower dimensional anti-Toshita space. So it's dual to some lower dimensional conformal invariance at the boundary.
See.
One
lower dimension.
One dimension.
I mean, where normally, because there are many Ds, if you had ADS D plus 1, normally you would have had a D-dimensional CFT. Here you have D minus 1.
Yes.
Okay.
Yeah.
Okay.
So thank you very much.
Okay. Thank you.
Yes. So this can be applied to a completely gapless situation, but depending on the choice of this end of result, we have some gap only at the boundary. But always in the inside this bulk region, M region, is always we keep conformal invariant. Yeah, thank you. Question? And so to derive this boundary condition, we just usual Einstein-Hilbert action. So this is Einstein-Hilbert action. And there is a Gibbons-Hawking term, but also sometimes, this is actually useful in my later part of my talk, we can put some matter localized on the brain. Maybe it is, can be smeared, but let's do some zeros approximation that this matter is just localized on the brain. So you can put some scalar field or gauge field or anything. So then we take a variational principle, we take a variation of this action, and then we, of course, we use extrinsic curvature, which is just derivative of covariant derivative of unit normal vector. So we always take unit normal distance outside, outward. And this and the whole special case of gravitational normal coordinate, which are often useful, is extrinsic curvature just computed by derivative of this law. It's as usual. But the point is that we take a variation, and then we end up with this formula. This is, of course, quite well known. And this is actually the reason why we put the Gibbons-Hawking term. So without the Gibbons-Hawking term, we don't have a nice variation. But if we with the Gibbons-Hawking term, we have a nice variation. Just this curvature, extrinsic curvature term with some matter contribution, and time delta H. H is induced metric on the brain, on the end of the brain. It's a variation. And this should be 0 to make this variation principle make sense. But one choice, of course, delta H equals 0. This is just the usual Dirichlet boundary condition. But we don't want to take this one for some reason. Okay? So we want to take this coefficient to be 0. This is usually Neumann boundary condition. If we think this is a scalar field, normal derivative of scalar becomes 0. This is Neumann condition. And this is sort of gravitational version because K is derivative, normal derivative of the metric. So the end of the world brain, so claim is that end of the determined by this equation. This is kind of a boundary analog of Einstein equation. Or in the context of defect, this is basically same as Israel junction condition. And this often appears, of course, heavily used in the context of brain world scenario. So the reason why we assume Neumann boundary condition, not Dirichlet boundary condition, because the following things. So if we think really, first of all, if we think this, impose some Dirichlet boundary condition, this is a really holographic dual, right? Its bulk is dual to some boundary, and this boundary, usually we put some Dirichlet boundary condition. So, but we don't want to regard endless word rings are somewhere where CFT lives. So it's more, we want to make it dynamic. So that's the reason, this is the first reason why we want to choose Neumann boundary condition. And another one, we can also find this kind of condition in special situation like Orient-Ford in string theory. Orient-Ford has a Z2 symmetry. Basically, K equals 0. This is a much stronger condition imposed. Maybe we can put also D branes on top of Orient-Ford, then slightly you can add some extra contribution. This is one string theorem, but especially in the case of ADS4 cross CP3, we can find it's dual to something called three-dimensional supersymmetric Chern-Simons theory, it's ABGM theory. In that case, we can precisely embed this construction into string theory. But otherwise, I should say this is a kind of, bottom-up approach. It's like a hard wall approximation. So I cannot justify more than that. But this often turns out very, especially ADS3 case, this really always gives exactly precise result. And the higher dimension is still non-trivial. So it's under investigation. But often it turns out it gives nice result. It's sort of maybe more than 10 years ago. So there are many works of application of ADS safety to QCD or condensed matter. Many people also do some bottom-up hardware approach. This is something like this.
So this stress tensor TQAB
yes.
is from the matter fields in the bulk.
Exactly. We take derivative. Yes. Thank you. Yes. Yes. Go ahead. Yeah. So in general, so we can put some brain. Then some in the bulk field also localized on the brain. That sense, not necessarily precisely on the brain, but we can just do approximation that everything on the brain. Then everything is very simple. So actually, this really comes from simplicity argument. In that sense, we are also doing this hard wall approximation. Basically. In general, it can be, it's smeared over the bulk region. Yes? Yeah. So this is the Brown-York tensor. Yes, this part.
Yeah, but it is, you said, the matter stress tensor?
So yeah, we can also add matter stress tensor. Just naturally, if there is a matter field on the boundary, then Brown-York tensor is given by this. Because we just derive by taking derivative of induced metric.
Okay.
So yeah, this is a Brown-York tensor. Yeah. Exactly. Thank you.
Thanks.
Okay. So this is a framework we work with. And so this is a summary. This is the same thing. So we claim that this boundary, some conformal field theory with conformal field theory on M, but the boundary condition sometimes breaks conformality. That's also fine. Just conformal field theory lives on M with some boundary is equivalent to gravity on this manifold N. So it's surrounded by this end of the word brain. This choice of end of the word brain determined by this Neumann boundary condition. So this is a ADS BCFT construction. So, but especially, so I mentioned BCFT. So let me briefly mention what's a BCFT. Let's remind. So this boundary conformal field theory. This is just a case with this is a conformal field theory with boundary, but with also conformal invariance on the boundary. So totally d-dimensional conformal field theory has a SO2, D symmetry. And if we go one dimension lower, we can have a SO2, D minus 1 symmetry. This is preserved on the boundary. This is in that case, we call it the boundary conformal field theory. If we impose just generic boundary condition, it completely breaks conformal invariance, nothing, but only fine-tuned boundary conditions satisfy this kind. For example, if we think some free scalar, then if we choose Neumann or Dirichlet boundary condition, it satisfies this boundary conformal invariance. But if we choose other massive like boundary condition, it breaks completely. And so this is one setup. So we have a time-like boundary. This is space, and my talk I'm focusing on 1 + 1 dimension, but this is you can generalize any dimension. But for simplicity or some other reason, I would like to talk 1 + 1 dimension. And if we send energy, it's completely reflected back. This energy, this means that TTX component is 0, and this is a boundary condition of energy stress tensor in this boundary conformal field. And we can also take a 90-degree rotation. So then this is a time direction. Then we have, let's think this is a Euclidean time direction. Then we have a boundary, this space-like boundary. So that's kind of, this defines state because this is a time and this is a kind of space direction. This defines state, and such a state is called boundary state or Cardi state, which satisfy this. This is a Virasoro generator, left moving and right moving. This is quite famous formula. And there are many also condensed matter applications, especially in the context of Kondo effect and so on. But I'm interested in more field theory aspects of this boundary conformal field theory. Okay, so now, but what about this? If we keep this conformal invariance, what's the gravity dual? So this is too generic to keep boundary conformal symmetry. Actually, it turns out that this important point is this matter part. If this is generic, it completely breaks boundary conformal invariance. But if TAB, this boundary energy stress tensor, is proportional to induced metric with some coefficient we call the tension, T is the tension. Then we can show that it's preserved conformal invariance at the boundary completely. And T is still one parameter. This is any parameter. And this T is in the end related to something called G function later. But this T, there is a degree. Up to that, we have this Neumann boundary condition given by. And then, so yeah, very simple setup is just kind of upper half plane. This can be any dimension, just Poincare metric. And we have X direction. We just treat X in special direction. And there's an orthogonal space-like direction, double coordinate. And we have a time dimension, time direction, and also extra dimension. And the upper half plane is defined by this one. Maybe this lower half plane, but this is just half plane. And we think this conformal field theory lives on here. And this is a boundary. And from the boundary, we extend the end of the word plane. This is Q. And it turns out, to solve this equation, it turns out this is just a straight line, just hyperplane, like given by this. So that way, so gravity dual for this boundary conformal here, say lives here, is dual to this green region, surrounded by this end of the world. Yes, yes.
So this choice TQAB proportional to the induced metric is something you are imposing because you get what you get, right? TAB.
Yes, yes. This is, we constrain the theory because so that it keeps boundary conformal invariance. Yes, yes, exactly. We are only focusing very special situation. Only there is a cosmological boundary cosmological constant term, then we can show there are symmetry. So could you say?
You choosing fields in the bulk which on the boundary satisfy this constraint, or are you imposing them?
Okay, in the bulk, let's see, no field in the bulk, no scalar field in the bulk, just pure gravity. And then, this because I'm talking about ADS3 case, ADS3 pure gravity. Sorry, I should mention this is ADS3 pure gravity I'm talking about. And we impose that this energy stress tensor is HAB and solve equation. Then it is easy to see there is a boundary conformal invariance. And we don't put any matter also on top of Q, only except this cosmological constant term.
This Q line on the boundary, is that a time-like line?
Q is time lag, yeah,
Okay.
because it's a time direction also this way. So this includes time direction, yeah. Q is time lag, yeah.
So if I understand, we are solving ADS3 pure gravity, and we introduce a brane which has some constant tension.
Yes.
And then this is the solution.
Yes, exactly. Yeah, exactly. And pure gravity ADS.
Units in which T is measured. I mean, T equals to 1 is special clearly.
Yes,
so,
good, yeah. So T should be, absolute value of T should be smaller than 1. So T equal 1 is really this guy gets to the nearby border.
Right.
So this means that infinitely many degree of freedom. And this angle is very important. So this angle is small. So like this, if T is negative, T equals 0 is really vertical in the middle. T goes -1, it's tend to this direction. And we lose a lot of degree of freedom. And so accordingly, G function is decreasing to -infinity. This is +infinity. And this is basically this angle or tension parameter as degree of freedom, which localizes on the boundary.
RADS units, right? You're measuring it in,
that's right. Yeah, order central charge.
So, and the T less than 1 condition comes from, is it some positivity condition or something? I mean, no.
In the context of holography, because we cannot find solution for T greater than 1. But actually, T greater than 1 corresponds to...
T equals to 1, for instance.
It's a really coincidence.
Is the Z equals to 0? No, so what is that? I mean, I'm just trying to understand, is that barrier from the point of view of the matter fields, what kind of condition is that?
I see. But for any T, for example, null energy condition always satisfied for any value of T.
Okay.
And also, T greater than 1 is okay, but then brane takes different form. It's Dojita brane. It becomes, this is anti-Dojita brane, and it intersects with boundary in space-like way. And when T smaller than 1, it's always intersects with time-like. This kind of topology change like thing happens.
Maybe just another thing to add is, in this case, the graviton is in fact massive, right? And there's the mass of the graviton is proportional to T.
Yes.
Right. But just if you did a bulk computation, this Porati kind of computation, you'd find the graviton picks up a mass because of these boundary conditions, right? And that mass is proportional to T. So in the case where T goes to 1, I think the mass will go to 0.
I see. 3D. But 2D.
So you'll have more, no, it's a 3D graviton. No?
Okay. 2D case, I think we can approximate this gravity by Liouville gravity. It's like a completely induced gravity.
Isn't the bulk here 3 dimensions?
My talk I'm focusing, but here it's general. It's general. So in higher dimensions, there's a
boundary
gravity.
Sorry.
Higher dimension, right? We have a massive gravity. But ADS3 case, this is 2D. So
So in ADS3, you have a two-dimensional boundary with a two-dimensional CFT with a 1D boundary, right?
Yeah, 1D boundary.
But even then, isn't it the case that the stress tensor picks up an anomalous dimension?
But there's no dynamical gravity here. So
it's a boundary graviton, but does it pick up a bulk gravitating mode because of the boundary condition? I mean, it could be, the massive gravity has more degrees of freedom than...
I'm not completely sure because we describe this gravity by Liouville gravity, and this is a bit different from usual gravity because we integrate that matter degree of freedom. Then this this grain world is like induced gravity, so there are no chaotic term originally.
Yeah,
I
see.
But I think what you are correct in higher dimension ways.
I see. I admit I haven't thought about the three-dimensional case in detail, but the general argument is that that stress tensor on the purple line would have satisfied d mu t mu nu is equal to 0, and now it doesn't because of because you have the energy can leak, and so I would have. Oh, you're saying? Oh, I see. No, I should think in terms of the effective one-dimensional.
Yeah. Well, 1D, yeah, maybe 1D gravity, maybe.
I see. Okay.
It's like a G function, boundary state. Sorry, boundary entropy. In terms of Cardi, it's a different boundary condition. Yes. Different boundary condition. But we only, this is a very coarse-grained picture, so we only look at, we can only compute the G function. Yeah, thanks for questions. And so here, this is a rough sketch. Another, aspect, yeah.
Sorry, Tadashi, I missed up the D. I just want to go back to this. So what is understood about the graviton mass in this case? As you say, in higher dimensions, it's massive. And what is the understanding in this case if one does this?
ADS3 case?
Yes.
In the case, I think in our earlier paper, we claim this effective gravity is given by Liouville gravity. So I don't know how we can call it a massive, massless or massive, because it's like, again, topological theory.
I see. And this takes into account these leaky boundary conditions. So even after you take into account the one loop effect, you can incorporate that effect.
Yeah.
Because in higher dimensions, that's what adds an effective term.
I think so. This is so another aspect which you recently often use is like double holography. So this we explain this setup. So gravity dual of this conformal field theory with boundary given by this setup. It's anti-Doshita space surrounded by M and also Endow's world line. But this is we can regard this as a setup of brane world. This is Cauchy-Randall setup. Then there is a gravity lives on Q, and it looks like a CFT coupled to gravity. But this is again because this is a gravity which lives on this anti-Doshita space. We can do ADS CFT, then go back to this original one. So this kind of, three kind of different picture is equivalent. But this of course this bit rough sketch, and we need more details. These details are not completely understood. As far as I know, it's not completely understood. But this is often used in many contexts of island or black hole, and also other cosmological setup and so on. So this is called double holography. And we can also take a special case of this guy. So we can put we can sandwich this space-time with two ends of the world line. And this is a boundary field theory, boundary conformal field theory leaves, but we can squeeze size of M, and then we end up with this kind of triangle situation. So then we can see this original ADS, D plus one dimensional classical gravity on ADS is dual to this gravity on Q1 and Q2 with M, but M squeezed to zero size, just Q1 union Q2. And then we can again use a similar argument that because this is ADS, so you can map this gravity on Q1 to some degree of freedom CFT lives on sigma, and then we find some codimension to like holography. This is something we call it wedge holography. Okay, so now I would like to go to more, details, like especially related to some G theorem. So before that, yesterday I talked about this.
Sorry, Tadashi. About these double holographies or wedge holography. So when you say it's not well so is there a dictionary then, like in the usual ADS CFT? Is there a dictionary between operators and?
Yes, but we don't know precisely what kind of gravity this is. So we expect this theory is to be quantum because dual theory is classical. We supposed to be this quantum gravity. But we, for example, if we want to write down Lagrangian of this theory, I think still complicated. So brain world people write down Einstein equation, how Einstein equation modified in such a situation, but it's not completely solved in my understanding. Yeah, that also, yeah. These are anyway, I mean.
That question one could also ask about the previous setup. If you could find realizations in string theory, which really give you these duals, even the ones you had in the previous slide.
Yeah, but the special case only in special case, if we use orange fold, we can realize it.
Will almost be t equal to 0 or something, right?
T equals to that, right.
So Oriental is t equals 0.
Yeah.
But if you want non-zero t,
but maybe
then
you can put some brain, D brains, the O8 brain, but we can put some D8 brain, and then slightly you can change. Yes. Yeah, orange fold has a okay. What is it? Negative tension. Yeah, negative. Yeah, but the string theory embedding is not so clear. That's right. Yeah.
Interrupt you, please go on. But afterwards, but of course, for the original Randall theorem, there's a very nice realization through fluxes and the deformed conifold and so on, right? That's not quite, I think, what you guys have in mind, but that certainly can be realized.
I see. Yeah. Thank you very much. Yes.
The way the
Yeah. Yeah. Maybe we need a culture Randall version. That's for because we want some Untitled Chapter brain. So a little bit need to change it, but maybe that gives some nice embedding. Yeah.
Maybe.
Thank you very much. Yeah. Sorry, I'm not really focused on bottom-up approach. I'm not going to talk about string theory. Yeah, that's very interesting point. So yeah, also this entanglement is very important in this kind. So in the end we change this formula, we extend this formula, but this picture looks similar maybe. So you might wonder that maybe these two guys are very similar. So we talked about this guy. Right? We talked about the ADS-B CFT, which means this field theory lives on M is dual to the gravity on N, and the entanglement entropy calculation, well, entanglement wedge idea is this region A is dual to some reduction matrix on A is related to this region MA. But these two are completely different. First of all, dimension is different. This surface is codimension 2, and this surface is codimension 1. And more than that, its boundary condition is completely different. This case, we just impose extremal surface. So this means just trace part of extrinsic curvature at 0. There is always solution to this picture. You can just fix a particular metric, any complicated metric, you can always find extremal surface. But this is no longer true. This is actually a big problem for ADS-B CFT. So we all have to fix all components of extrinsic curvature. So if we just fix background, not necessarily exist such a solution. For pure ADS, if there is a nice symmetry, some group theoretical structure, some cosette space, then we can always find such a nice solution. But otherwise, it's, for example, ADS black hole, a higher dimensional black hole, we cannot generically find such a solution. And that means, but this is not a problem because this Q is a brane, so it backreacts. It changes the metric so that it makes this boundary condition satisfied. So we have to modify the metric. So it's in generic case, it's very complicated because it becomes like numerical relativity like thing. So I just focus on solvable case in this talk. So these are the crucial difference. I just wanted to, but it is interesting to combine these two ideas. That's actually plays very important. So that is exactly this one. So what about holographic entanglement entropy in ADS-B CFT? So there is one new ingredient. So naively, the formula looks same. So we talk about this manifold M, CFT lives on M, and we pick up some region A. And we are talking about gravity dual is ADS, some part of ADS which is surrounded by this end of the world, right? This wedge region. And we want to calculate the entanglement entropy for region. So naively, we can find some minimal surface which covers A like this. But actually, there is one more choice that actually we can end on some region on Q. Q is a dynamical, has a metric. So actually, we can end, this minimal surface can end on any region. So this is called B. But we have to extremalize to satisfy Einstein equation. So we minimize or extremalize against this choice of B and also choice of surface gamma A. So this is a correct prescription. And one intuitive way to understand why we need this guy is a mirror method. You can think about if we calculate one-point function with boundaries, so it's essentially leads to two-point function. So this is a kind of mirror charge. But also another way to more modern understanding is just this is island, because island also takes this exactly same formula. If we regard this a classical version of this island formula. Island formula I mentioned yesterday is like area of, if there is an island, this is the area of island plus a union sigma. This so let's identify B with sigma. Sigma is island. And this is a quantum formula, but we can use ADS CFT. This is a higher dimensional picture. It's mapped to this kind of special case. It's mapped to this kind of classical expression. So this is one way to understand island formula from gravity dual with boundary space.
I didn't understand something. So who said that extremize over B?
Yes.
Is like satisfying Einstein's equations. That's not clear.
So yeah, we put some in the replica calculation. We put some deficit angle here, and we need to smooth out. But I have in mind some Lukowitz-Malda-Senard type argument, and that can be end on any surface. And we extremalize Einstein-Hilbert action, so that in the end gives. If we have a deficit angle, basically it gives area, and we extremalize action, so that roughly gives. Yeah. Thank you very much. Yes, that's what we expect. Okay, so the simplest example is like this: ADS3 BCFT2. So this is a BCFT. So we are on the lower half plane. Configuration lives on lower half plane. This is a space direction. I write it tau, but it's not time. It's like just space direction. And t is also a Euclidean time direction, but it's like space direction. So it's like completely Euclidean setup, and we pick up subsystem A. So in that sense, sorry, this is a Euclidean time. You can say this Euclidean time. So we have time slice, and this is subsystem A, and this complement is here. So complement B. I have in mind this setup. And we calculate entanglement for A, and then we have this boundary. So we write geodesic. This is a extremal surface, and this guy can end any points on Q. So we extremalize over the points on Q, and then we reach this formula. Actually, this turns out just semicircle. This is some arc of some round circle. So you can choose this point, then it's like larger length. So, and that gives, because of this angle, it's a result, of course, depend on angle, and it's really controlled by tension, because tension controls this angle, as I mentioned. And this part is just regular divergence. We have only one boundary of 3/6, that logarithmic divergence, but plus constant. This constant is interpreted as a boundary entropy. This is or a G function. So it's really depend on T. And if we T equal 1, this goes to infinity, and the -1 goes to minus infinity. So there is a bound of tension, plus minus 1. But of course, tension is scales like in central charge. I think it's quite boundary entropy of scales like central charge is a very huge value. So it's not clear. Real boundary conformal field theory maybe only covers only part of the region. So this is still open problem, but it's a very huge window over the central charge.
Hello.
Yes.
Can you go to previous slide of that island formula?
Yes.
So yesterday there was the same formula, but there was no boundary CFT. So how it is different from this?
No boundary. Okay. But boundary. So there is a boundary CFT, but we can regard this boundary CFT as dual to some gravity on untitled space. So that is a Q. So then it's much like island formula. Island formula means there is a CFT, but also is coupled to gravity.
Okay.
But very heuristic argument. So.
Central charge, the boundary G function does not scale with n. It doesn't scale because this seems like it's order 1, right? It's 1 plus t. There's a C.
Order C.
To the power C.
Yes.
To the power C.
Yes. Order C. Yes.
Okay. So there's. I see. Okay.
Yes. It's order.
In the case where the boundary in the CFT was a time-like boundary, was in the time direction as opposed to in the space direction. Is there an interpretation of these tensions?
Time boundary.
Yeah, yeah.
The Lorentzian time.
No, let's say
Euclidean
the boundary is at some constant value of Euclidean time.
Yes, that's interpreted boundary states.
Right. But in that case, how do I interpret the tension?
It's a coefficient. Okay, boundaries maybe. Yeah. So it's like so we have boundary state and ground state. It's take overlap. This is basically G. Up to some normal, regularization. This is a disk partition function. And this is actually original definition of G function. And the boundary entropy is log of G, which is, appeared here. Yeah.
I mean, this is independent of the boundary conditions that you are putting on the...
So it's dependent, of course, it depends on tension. So it's really parameterized. This angle is related to tension, and this really corresponds to different choice of boundary condition. Yes. Yeah. So yeah, that sense, it's really, there is a boundary condition dependent, and this is alpha dependency. Thank you. This is parameterized by tension context. Okay, so now I come to G theorem. So, but before that, I want to explain C theorem. This is a well-known fact, but just let me start. But to pick up central charge, actually in numerically, it's also looking at the entanglement is quite powerful. So many, I think, quantum many body researchers are doing actually numerical calculation. So we can calculate the entanglement, then logarithmic coefficient at the critical point turns out to be central charge, C over 3 or 1 into this C theorem. There is a central charge basically describes the number of fields, degree of freedom. But if we talk about the renormalization group flow, we add some relevant perturbation. Then you can imagine the massive perturbation. It's in the infrared. Its degree of freedom decreases or vanishes in the infrared if there is a mass gap. And more generically, if we turn on some relevant perturbation, we expect degree of freedom is decreasing under RG flow because we are coarse graining under the process of RG flow. And accordingly, so this central charge, which if this is a really nice quantity, which measures the amount of quantum fields, degree of freedom, then central charge also should decrease, and as proven by Zamochkov in a famous paper, so we can prove this. It is like most fundamental inequality in entanglement entropy, and also somehow analogous to second law of thermodynamics. And that you can see from this, we can derive this from monotonicity of relative entropy. Relative entropy is defined by this way. This basically measures distance between two different density matrices, rho and sigma, rho log rho and minus rho. It's not symmetric, but this is quite useful. It's always greater than, this is not always non-negative quantity. It looks like distance in that sense. And we can, and monotonicity of relative entropy means that if we coarse grain, maybe taking a trace and so on, it's this relative entropy always decreasing. This is, we can exactly prove this in this is, for example, in a proof is in Nielsen-Chan's textbook, and we can see derivation of this. And this is quite a basic inequality. And this also, we can also use this to formally derive second law of thermodynamics. But anyway, yeah, so we can have a low ABC, and we can just take this combination somehow. And then we trace out C, that's of course coarse grain. And that means more difficult to distinguish two different states. That's the reason we have this monotonicity of relative entropy. And we have this, just trace out C, or just cut out C, and we get, and this is obvious, this is larger. So that case, this is just equivalent to this one. So you can just plug this in, and it's very easy to compound. This is the one direct way to think strong subactivity. But anyway, so this is, it seems to be very important inequality. As far as, for example, look at just, textbook quantum information theory. So, and also it's quite useful to understand holographic duality, and that comes from triangle inequality. But we can, so let me explain. So first, this Cauchy-Freitas entropic C theorem. So we have this inequality. We just rewrite this, and we allow A and B has an overlap. We call this A, this is B, and this is A union B, and this A and B overlap of A and B, like this. We can rewrite just this way because somehow this is useful. So it's like this. And we apply, so this strong subactivity in 1 plus 1, we assume relativistic invariance. So we need also, we assume unitarity and so on. 1 plus 1 dimensional Lorentz invariance. And also, of course, we are focused on vacuum, so it's translational invariance. Lorentz invariance, translational invariance, and unitarity. And we choose subsystem to be slightly tilted. This is the time and the space. Important point is we choose some boosted subsystem. This is still okay because Lorentz invariance, we can map this to just regular time slice. So A and B is like this. Then it is easy to see that this region, this green guy is A union B because any signal which comes from here, it's intersect always either A or B. But the signal which come from A and B as always intersect. Both of the guys always intersect with A union B here. This is a right cone, null right ray, null cone. So this we can apply this strong subtlety to this setup. And also geometrically, we can easily see this length A, invariant length, Lorentz invariant length, A times B is the same as this time. It's very simple geometric relation. And this is actually proves C theorem because of the following way. So if we let's take just for simplicity, we can exponentiate length. A union B is exponential x, and A cap B is like overlap is exponential y, and Ax is greater than y, of course. And then A and the size of AB, which we take some symmetric guy, that means the length of A and length of B is the same. Let's take a very special symmetric situation. Then this equality says that it's exponential x plus y over 2. And now we remember this strong subjectivity, and then we have this inequality. This is something, of course, we often see. This is just concave. This means that entropy function is concave. So the second derivative is negative and non-positive. So and we know this at a critical point we have this expression. This exponential x is length. So this length, this famous formula. And if we take derivative of x because it's a log exponential x becomes x, derivative of Sx entropy, then it gives central charge at a fixed point. So it's very natural to regard central charge, effective central charge to be derivative of S. Maybe you can multiply 3. So this is an entropic C function. It's a C function that means central charge defined even when non-conformal point. And then this second derivative non-positive means that this derivative of central charge is also non-positive. And this is an entropic C theorem. Yes?
Was unitarity important in this proof?
Yeah, of course. Yeah. Because strong subjectivity, only true when we have a unitarity. So we assume positivity of Hilbert space and so on. Yeah. Also, central charge can be any negative or imaginary for generic case. Non-unitary case, so it's not so easy to see. Okay, so what we would like to do is to generalize this to this proof to G theorem. But before that, let me also remind what was the G function. Already I mentioned a little bit, but more precisely like this. There are 3 different definitions. This is first introduced by Affleck and Ludwig. Ludwig basically talk about this 2 definitions. So it's like basically I write it here. It's like it's a disk partition function with some boundary condition alpha. It's called G alpha. And this coefficient also appears in the equivalently in a cylinder amplitude. You can think about cylinder amplitude and there's a 2 boundary, and they are separated by length L, and L goes to infinity, then only ground state propagates. Yeah, in terms of closed string language, it's a closed string only ground state of ground string propagates. So if we calculate this amplitude is equivalent to this one, this boundary state, and the Hamiltonian evolution, and this is factorized into this way, G alpha, G beta, and some lowest, this E0 is a ground state energy. And from that, we can explicitly read off value of G alpha. This is actually convenient because for this, we have to renormalize this amplitude. It's the original UV divergence, but this is in boundary state, we often have already renormalized formalism. So it's very useful. But obviously, these 2 are equivalent. And finally, as first noticed by Calabrese and Cardi, and this G function appears in the context of entanglement entropy. This is actually, we're going to use this one. This is basically what you can derive by replicatoric from these facts. And so it's like, if we talk about CFT and we have a time evolution, and this is static, so we just focus on vacuum state, and A is subsystem A is taken to be this point to really at the boundary. This length is L. then it turns out to be entanglement entropy is this guy plus the 2 log L, because we can imagine some mirror method. There is a twist operator, its length 2L, and just half contribution C/6. But there is an extra contribution which comes from boundary degree of freedom. This is a G function. In replicatory, this becomes just, again, disk partition function, so that's the reason we have log G. So now, then what G theorem tells us? So G theorem is analog of C theorem for this G function. So at the UV fixed point, we have this nice G function of boundary entropy, and we want to interpret between boundary renormalization group flow. So the Affleck-Rudolph claims that this G function, there is a G function which monotonically decreasing under RG, boundary RG flow, and they construct such a function in perturbation theory. And anyway, the G function, definition of G function according to them is just disk partition function, or even if we have a non-conformal boundary condition. And we start with UV fixed point, and we add boundary RG flow, some boundary relevant operator, and just see this how a partition function evolves.
So does G also appear in a relative entropy or in some other UV safe quantity? I mean, is there
a relative entropy?
Yeah. I was a little worried just about the interference in the previous slide that you had between the cutoff epsilon and G.
Yeah.
So is there a UV safe way to define G by means of a relative entropy or something?
Yeah, this is true. So it's contaminated by this UV cutoff. That's right. Yeah, I'm not sure. Sorry, I don't know much about this relative entropy with boundary. Maybe if we talk about some, we can relate this to real UV finite quantity. Yeah, thank you, but I don't have a. Yeah. So okay. So now, then, Frida and Konecny gives a field theory proof, but just taking disk partition function and flow it by some boundary RG flow. It's a field theory proof, and there are also quantum information proof by using relative entropy, but again using boundary RG flow. This is not like previous Cassini-Freitas argument. This is Cassini's paper, but it's different, completely different thing using some property of relative entropy. And also there is a symmetry argument by Komorowski and collaborators. But nevertheless, we are quite interested in this original proof like this. This one, very simple proof, just one-page proof. So we want to do this in a G theorem because that may be, good thing is that we can we can give G theorem to some geometrical interpretation. So this is what I want to give here. It's our recent work. And also I will give some holographic interpretation later. So anyway, so we use this fact. So at the fixed point, always this G function appears, but we also define G function at non-conformal point by this equation. So we subtract this logarithmic contribution, and or we just pick up some finite contribution. We always call this a G function, even if there is a non-conformal invariance. And we will show this log G is decreasing, monotonically decreasing under size of subsystem A. So L is the only scale in this theory. So this is we can follow this time evolution, sorry, L evolution, length evolution for this. This is analogous to the entropic C theorem because we change the size of subsystem.
So if it's not a conformal theory, then just the bulk part won't be a log function.
So this part is, okay, because bulk in the bulk always we keep conformal invariance. We only break conformal invariance at the boundary. Yeah. It's G theorem. We always assume bulk, conformal invariance, and only we turn on some relevant partition or localize on the boundary. Yeah. Thank you. So, but there is actually, so this is actually, one might think this is very easy, but it's actually highly non-trivial. And to get to the correct answer, we have to notice two simple but very important facts, very somehow non-trivial facts. Yes?
You define G as
huh?
You define G as
Yeah.
So where is L in G? It seems like it's...
L in G is, okay, so it's
this I can define without any subsystem.
L is sort of, RG flow boundary set. But you are right. So our definition is just really based on entanglement entropy. I'm not talking about this definition, this partition function definition. I'm using this one to define G function. Only if UV fixed point, this is exactly the same one. So we can define G function like this. This is exactly same as this one. It's guaranteed if we talk about UV fixed point or IR fixed point. But otherwise, this guy is no longer same as this guy. So yeah, you're right. So we are changing this definition of G function. Yeah, that's important. But anyway, so entropy also, that's same thing also, C theorem. So C function, candidate of C function depend on the definition. But only UV fixed point, they give same result. So yeah, so the two important things, this is one thing is just if we have this subsystem A and entanglement entropy A is same as A prime. Sorry. Yeah, so A is, so this entanglement A is same as this tilted guy, because this is, you can imagine some also taking this mirror charge, mirror method, then this slice and this slice the same, define same Cauchy slice. And also you can think also some particle propagating here, if it passes through A, it's completely reflected, always pass through A prime. This is really, we assume this is completely reflective boundary condition. So that sense, even though it's tilted, it's always same value. So the entanglement entropy for this kind of subsystem is only determined by X coordinate, this length.
Can I ask a question?
Yes, yes.
Why can you assume complete reflection?
Sorry?
Why can you assume complete reflection even though you're considering non-conformal boundary?
Yeah, because we are talking about rigid boundary condition. We don't put any degree of freedom on the boundary. Yeah, okay. It's energy conservation. Energy flux. Yeah. Yeah, if there is a degree of freedom, the situation changes. So this is a kind of, this is kind of like interface rather than defect. And the second point, also this is also quite important. So if in general, we encounter this kind of setup with boundary, but with somehow tilted subsystem. So it looks non-trivial because it depends on many different coordinates. So maybe we cannot simplify inequality, but we are taking special limits so that these two guys are right-like separated. So that case, effectively, this length is very small if we go back. So we can actually confirm this in many examples that actually this, in that limit, if A very close to the line, it's just approximated by usual formula as a vacuum state. So we can neglect the contribution from the boundary. So these two are very important ingredients. So now we want to prove. So previously we assumed this kind of very symmetric choice of AB, but this is doesn't work. So we choose this. There is a boundary. Also we really attach this triangle at the boundary, but it's tilted. And in the end, we boost setup with infinity to make everything simple. So you use this fact. So we started this kind of generic setup. So this is a light cone, light rays, and this is SS, and this is middle UU. Just many parameter pairs. So this A and like this, B and like this. This is a coordinate. B is this time coordinate, and this W is this time coordinate. And so A, B, so there is a two class of the entanglement. This guy and this guy is a really double kind of interval. And in the end, we take a boost to make this simple. And A union B is a really attached at the boundary. We can use this fact to, these guys, A and A union B only depend on X coordinate like this. And these guys are, at first, it's non-trivial. So first thing we do is to take this U goes to S limit. We this point is very close to this one. And then, so this A union B, these guys looks right-like. So we can approximate it by these formula. This is just ground state formula. We just compute the length. It's a well-known formula. And also A and A union only depend on this X direction. And in the end, we end up with this. This should be positive according to strong subjectivity. This combination looks like this. And then next thing, we are attempting to take B goes to W to make this difference as a real derivative. That's what we do. This is okay to do this. And then we find this derivative is, because we appear, this is the derivative of this entropy. So we have this constraint. This is almost answer. But L is defined by this. But we can take also, furthermore, take limit that this S is very, very small. This triangle is like this. This is also okay. There are nothing prevents us. This S goes to 0. Then we can give a most strong bound, tightest bound to S goes to 0, we get this. And this is the unsuck shape. So because we define G function as a entanglement, disconnected entanglement, as an entanglement entropy minus this log divergence. And this guy, C/6, cancel this guy, and then we reach this G function is always decreasing under RG flow. So this is the entropic difference. So again, this kind of triangle picture is very important here, but we have to take a boost. So we can generalize this to a more complicated setup with defect line. Again, there are no degree of freedom, but there is a defect. And we can also change central charge. This central charge is equals C1 and C2, but still we can use this kind of triangle argument by double copy. It's like mirror-like method. Double copy of that. I'm not going to detail, but we can derive this equality. And this C is like an average value of C1 and C2. So we can also derive this. And yeah, now I go to holographic calculation. So far I don't assume anything about holography, just talk about on a few theory. And now we would like to reinterpret these results from holography. So first of all, anyway, strong subjectivity is very important. So strong subjectivity in ADS CFT can be easily derived, or at least for static background, but also we can have a time-dependent background, but as shown by Alan Wall. But that's also important later. But let's think about static case. And we can, in ADS BCFT, we put some end of the word brain like this. This is ADS boundary, and this is a bulk. And we can put some holes, these holes, or this kind of end of the word brain. This is end of the word brain also. And this is end of the word brain. But still, we can show that this strong subjectivity is true in static setup. Basically, proof is the same. We can just use triangle inequality to show this. So static background, strong subjectivity is somehow, in other words, automatically satisfied in ADS CFT. So, but that's, confusing. At the first sight, this is a bit confusing because in static space-time, G function, so we have some boundary. So this is the ADS boundary. And so we can take this surface Q, this end of the world brain, and maybe any shape. Still, any shape, this strong subjectivity is satisfied. But this angle is really G function, and G function should be monotonically decreasing. So this guy may be okay, but this guy is not good. Like way. So it looks, at first, it looks confusing. So why G theorem can be derived in ADS BCFT? But actually, for that, actually, we have to think more time-dependent. Some Lorentzian, we have to put some Lorentzian nature. That will come in. And but anyway, calculations can be done in a static setup. So we talk about this X direction and this Z direction extra dimension. And we just take any shape of end of the word brain. This red curve is the end of the word brain. And we take subsystem A to be this length L interval. And this point is P. And we have some entanglement that will be computed by this length of this geodesic, which end on the end of the word brain. We have to extremalize over these points, but P. This point, let's parameterize A, ZA. This is very elementary geometry. So and we just calculate this length. This is, of course, should be. This is a pure ADS3, so it's a part of circle. In minimal surface in ADS3, geodesic in ADS3 is just always circle. In this context, it's just part of circle. So we can do this calculation. So first of all, we can relate this point L. Sorry. We can relate this length L to this value of A, this point. This is just given by this equation. And we can calculate the geodesic length because it's just part of an arc of a sphere. And then we can calculate this, this combination appears in this monotonicity, this argument, right? This one. So we are interested in this quantity is negative or positive. So this turns out to be this guy. ZA is, of course, this function, this Z equals ZX, this function, and this combination appears. So, and strong subjectivity satisfied if this is non-negative. And actually, we can show that if we talk about, as long as we change the subsystem in this setup, it's not so easy, but you can actually see this by imposing null energy condition on the end of it. That's actually now this kind of Lorentzian nature appears. So, I mean, we have end of the variable, we have time direction, and we assume this energy on this null energy condition on the brane, that actually second derivative of these minus second derivative of z is actually positive. So you can take derivative. So at a equals 0 limit, this is you can approximate this guy as this guy, Taylor expansion. This is 0. And that means second derivative is important, and this is because negative, so this is becomes non-negative.
I'm sorry, I didn't follow the details here, but would you use much about the nature of the time-dependent situation?
Okay. I'm using only null energy.
Seems like as long as you have some time, you had a time-dependent background here, or
good question. Actually, it's really good. Because actually we are boosting system. Then that part is actually we need to talk about time-dependent holographic entanglement. That actually plays very role. And to make this time-dependent entanglement and to be satisfy strong solidity, we need null energy condition. Yeah, so it's a bit complicated here, sorry, logic, but yeah. So
later, to understand the definition of time-dependent.
Yeah. I said. So yeah, anyway, we have a not trivial, I mean, end of the world brane, but we boosted it. So for this observer, this looks like time-dependent. So, but for that, of course, we should impose the strong subjectivity, and then actually we need a null energy condition. Yes, thank you. Yeah, so it's a bit complicated logic. Yeah, but anyway, yeah, it works very well. And also, G0 is very important to see some sort of topological censorship, because if two guys, this A and B, let's assume time direction and everything static. If we can connect A, B, they are separated at the boundary, but maybe connected in the bulk. This is like traversal wormhole. This is, of course, we don't want the safety, but this kind of configuration prohibited by G function, because G function, the theorem, null energy condition tells us this always decreasing. Angle should always decreasing. So this is not allowed. This kind of bending, this concave-like function is not allowed. So also the theorem actually prohibits this kind of traversal one.
Intuitively, total amount of area should decrease. I mean,
yes.
So the degrees of freedom get.
Yes. Exactly. Intuitively, yes. Exactly. Thank you. Okay, so using the rest of time, I'd like quickly talk about some explicit example of ages BCFT, but where end of the world brane have some matter on top of that. And the simplest matter is the localized scalar field. We can also make other more complicated model to maybe describe some interesting condensed matter like setup, but yes, it is.
The question is actually a slightly vague question. But in these effective end-of-the-world brane setups, sometimes you naively find inconsistencies even with the null energy condition. For example, there was this claim that you could find shortcuts through the bulk sometimes. If you looked at the distance of the brane.
Yes,
and then it was found that if you looked at the full top-down construction with branes and so on, then those shortcuts went away. So could it be that there is sometimes you need more than just the effective field theory null energy condition, but something I don't know what that something would be, but at least in one case it was found that inconsistencies that naively appeared in this effective field theory setup went away when one considered a more sophisticated model.
Kind of on the brane, maybe. On the brane, there are causality violation.
So the claim was there was causality violation, but then if one considered a proper embedding within string theory models by trying to construct these setups more carefully, then it was found that causality violation went away in those examples. So I mean, could it be that sometimes for consistency of this kind, you need to put in more than just effective field theory and null energy condition?
I see.
Maybe it's a vague question.
Yes, we only look at our case. We only look at this quantity in BCFT because the causality should not be broken. But about the brane, I'm not completely sure. So brane theory is also non-local. Whether we really require causality, how much we can require that. I mean, especially the case where we combine these two systems like double holography, maybe it can break. I think there is a work by Ji Xiaowei, and who finds some breaking effect when we combine these two guys. But I think it's a bit highly non-local theory, so I have nothing to. No, thank you. Okay, so yeah, I just want to give some explicit example and what's the implication of this example. So normally we don't put any matter except when we talk about the renormalization group law in general argument. So we just usually talk no matter on the plane. So then we can have a very simple solution, ADS plane or DS plane. But I want to put this scalar field on top of this plane. So that's what we studied with these people. And so this is a very nice model because in general it's very complicated, but we are talking about focus on D equal 2, that means ADS 3. Then bulk equation motion is just Einstein equation. It's like always locally ADS, so it's very easy to solve. We can always assume some metric and just talk about the location end of the word plane. And only non-trivial thing appears this scalar field on this plane. So this gives some solvable model. So that's the reason we study this. And so the boundary condition now takes a boundary energy stress tensor. This is just the energy stress tensor of scalar field, the kinetic term, and we just have a potential term. And we actually, in this model, because we can choose any potential, so we can design any shape of end of the word plane. This is some technique which you use also when this ADS CMT like things are popular, maybe 10 years ago. So anyway, this is very simple. Huh? So this is case gravity dual of this setup. This ADS3 and is BCFT some conformal field theory with some boundary. This boundary breaks conformal mass in general, and we want to see some explicit example of boundary renormalization group flow. So this is exactly this model. So end of the word plane is not, if there are no matter, it's just always straight line, but it's now slightly bending. And following G theorem, because energy condition also should be true, also this model. And indeed, we can derive boundary equation motion like this. These two constraints just come from this guy. And this already showed that the second derivative of Z is positive. That means it's always going this direction. And G function is decreasing. So we have some explicit plot for particular choice of Z. This is a solution to this all equation motion, and the G function is monotonically decreasing. And this is a potential of which you use to find the solution. So it's come from here. It's a tachyonic. That means relevant perturbation and going down. And the scalar field from 0 to approach is constant. So this is one explicit example. And also we can more generalize, and we can somehow enjoy some non-trivial setup like this. This is a kind of disk setup, but we can find some this kind of donuts, like half donuts like setup by choosing this potential. And this case is at one boundary, it's here. The scalar it condenses and going back again at this point. And there are double renormalization group flow, so then we can find such solutions. Okay, so but more interestingly, so we can find following interesting phase transition. So this is actually a basic situation. So we have a cylinder. And we are talking about conformal field theory on cylinder, but we have two boundaries. There are two boundaries because the cylinder has two boundaries. And one boundary, we have one boundary condition, and another boundary, we impose other different boundary condition. So this is only possible because we treat this scalar field on top of that, and we change different value of scalar fields at each point. So the scalar field approaches phi 0 at one boundary, but this end of the word plane, the scalar field, and the scalar field approaches phi 0 plus delta phi. I mean, phi 0 is not important because we are assuming some massless and no potential to solve the theory. So phi 0 is not removed. The difference is important. So when we change the difference of phi, we find actually interesting phase transition. So this is in the end we find this phase diagram. So this is a temperature. Vertical line is the temperature, and the horizontal axis is delta phi. And the usual case is just delta phi equals 0. This is the usual ADS BCFT without any matter fields on top of the plane. And this is a usual Hawking phase transition, but with the end of the word plane. This is a usual Hawking phase transition. And that means this phase is thermal ADS phase. That means this plane, end of the word plane is connected, like it looks like confined, like setup. But if we go to black hole phase, end of the word plane disconnected and end on the horizon. So it's a kind of deconfined phase. But interestingly, if you also turn on delta phi, and if this boundary condition changes so much, then there is a critical point appears. So it's this guy is terminated at this point, and this is really quantum critical because of this entanglement interference I will explain. And beyond that, it becomes, but this is much like also similar to maybe QCD like phase diagram. But the point is that there is an interesting critical point, and here it's a thermal radius and BTG, but only this point Poincare radius appears as a metric. So it really looks like. Delta phi and beta, this the beta, and also this length delta x. So these are zero temperature, yes, and also delta x. Delta x. And yeah, the phi. Sorry, delta x is combined with beta, and phi is dimensionless actually. This delta phi is dimensionless because they are talking about massless. It's a kind of modular. This is exact.
Why is the special value picked out? What sets that?
But this is order 1 value somehow. It's not determined by other quantity. It's just come from model, I should say. Yeah, I don't know because there are no. This is not this is dimensionless. It's just 1 point something or like that. Yes, yes. So yeah, so this is the only thing we multiply central charge here actually.
Sorry, just to understand here V of phi in that figure you were showing was 0.
Yes. So only this part. This part.
So I guess that's your question.
What sets that order 1 number?
But this is order 1, but also maybe it's multiplied central charge here. Energy difference is the central charge. Yeah.
And when you hit that phase transition point, what does the end of the world brain look like? I mean,
It looks like like this, like this. But this horizon goes to infinity.
That's the point.
But it's anyway, it's kind of connected. This guy is connected. Yeah. Also goes to infinity, but it's connected. Yeah.
For other values.
Yeah, you can take this also limit of this guy. Anyway, it goes to infinity. Yes.
I mean, if you were not at the phase transition, is it like
but sorry, no. I think it's end on some point. Yeah. So it's like this. It's this horizon goes to infinity, but it's connected. Yes.
So it's not clear from just the locus of the brain what is
Yeah. Yeah, so we don't have a precise understanding what this means. But anyway, this means that we take two boundary conditions. We do same boundary condition, but we do some exact marginal perturbation for one guy, and then we see some phase transition. That's what. But we can have some intuitive argument by thinking. We can again take double rotation, 90-degree rotation, that this becomes time direction. This is what we do. So we can just basically what we do is just time evolution of this kind of setup. And then, so this guy is connected, this disconnected guy looks like this. And the time evolution have a non-trivial horizon. And this is when delta phi is small, delta phi is large, it becomes this kind of summary. Because these two guys are flipped because we did some we did some double weak rotation. So that case, this case looks very trivial. After double weak rotation, this becomes summary radius. This becomes BTZ. So it's like quite trivial. So under Lorentzian time evolution, there are no end of the world brane appears. But in this case where delta phi is small, then there is a non-trivial end of the world brane evolving. And especially delta phi equals 0 case, this is exactly same as something setup studied by Hartmann and Margasena, which is dual to global quantum quench. That is entanglement entropy. In this setup, it's typically linear about time evolution. So this is when this delta phi is small. But at the critical point, we encounter this Poincare ADS, and this is the end of the word brane. So this point is finite, but it goes to horizon. It's real-time evolution. So then we can calculate this length, and it turns out logarithmic growing. And if delta phi is greater than some critical value, everything becomes trivial. So there are no just entropy. End of the word brane disappear. So there are no time independence here. So it just entropy becomes constant. And this looks very analogous to what we know about entanglement phase transition, or more one model realized this is it's famous. One is called measurement induced phase transition. So you have some unitary circuits, but we put a lot of projections, and depending on how much we put projection, there is a phase transition. Initially, we have chaotic Hamiltonian like time evolution leads to linear T growth, like global quench. But when we put a lot of dissipating dynamics projections, it becomes logarithmic. And finally, if we have too much projection measurement, we have a lot of kind of decoherence, and it goes to entropy is finite. It's a very similar phenomena happens, interestingly. So in our case, but we put some end of the word brane, and this seems to give some non-trivial dynamics. But we have to be very careful, because what we are studying is like this density matrix, but this is not density matrix, because this is we have two different boundary state appears, and with some regularization and time evolution, but these two states are different. So this is a go beyond usual density matrix. It's much like something we call transition matrix. This is actually topics of my final lecture on Friday. This is something called entropy computed from this is something called pseudo entropy, rather than like this. So rather than entanglement entropy. But yes?
Very sorry, but I didn't follow the details of your double bit rotation. But isn't your system a unitary?
Good question. Yeah.
So the projections are not.
Good. Yeah, actually, you're right. That's actually important point. And here I should explain that. If we go to the Lorentzian signature, there is still end of the word brane, especially in this setup, or this setup. There is an end of the word brane. We are talking about this region. We always zero temperature, but we're talking about around this. That case, actually, scalar fields takes imaginary value. It looks really non-unitary. So otherwise, if we don't put such an ingredient, it's always, we can easily see that always entropy is linearly growing. So this coefficient changes a little bit, decreasing if we add some scalar field, and that's really introducing non-unitary effect. Yeah, so there are some such a similarity. But not exactly same in that sense, because this is not regular density matrix. They're quite interesting how precisely related. But anyway, we can, yes? Yeah. So we did some double Wick rotation. So we changed the name. Yes. Yeah, here it's a complete space-like. This is a space, and time direction is somehow also one. We now regard, yeah, exactly. Yeah, sorry for. Yeah, anyway. So yeah, so I'll explain this pseudo entropy in my final lecture. But anyway, for that language, we have this kind of phase transition. So this is BTZ and Poincare and stuff. Yeah.
Can you go back to the formula of the entropies that you computed in this state? So you're computing entropies for this transition matrix, which is not
that's right.
which is not positive, but still the entropies are real. Yeah. Is that surprising or?
Yes. If somehow we can rewrite this in terms of path integral language, then everything's real value somehow. Because also scalar field becomes imaginary value, but it contributes to the metric because square, right? Del phi square. So it becomes real value. So because of this kind of nice kind of cancellation, everything becomes. But if we are also considering about some other setup, but a slightly different model, then it can become, complex value. So it's just kind of coincidence gives this, yeah. But anyway, that means this model is very special. Okay. Yeah, I think this is basically that's all. And so here's a conclusion. So we talk about strong subjectivity can prove this G theorem. And also we have some holographic counterpart of that. And where this narrow energy condition plays an important role. And also I discussed about the explicit example of boundary RG flow by adding scalar fields localized on the brain, and also talked about some, if we have two boundary with different boundary conditions, we have some entanglement based on this like phenomenon happens. So yeah, there are of course maybe more about future direction, but what about higher dimensional generalization of G theorem? Can we prove it in strong subjectivity? Because we can prove F theorem in strong subjectivity. Also, what about we might get some non-trivial constraint for time-dependent cases from strong subjectivity. Also, it's quite interesting to think algebraic recent development, thinking of recent development of algebraic quantum field theory and its entanglement properties. Maybe we can also get a more rigorous approach to C theorem and G theorem. Thank you very much. I think I'll stop here.
So can you have something like end of the world brain dual to interfaces? For example, if you're doing a CFT on a compact manifold and you choose some.
Yes. So we have some gravitational spacetime and put the brain in the middle, and that is a dual to interface. Yeah. There are also many works in that direction. Yeah, two different. Yeah, so we attach these two different. And the boundary condition now takes the forms of Israel boundary, junction condition.
So in ADS3, is it possible to have a top-down, I guess it's called, top-down construction of this boundary holography? Because now, in say the symmetric orbifold CFT or something like that, can it be possible to, because that seems like a case, ADS3 is where it is best understood in terms of even the boundary CFT and so on. So has there been any attempt to understand this double holography in that context in the D1, D5 system or the dual NS5 fundamental string system?
I see. Yeah, that's very interesting. Direction. So far, yeah, we didn't work.
No one has made the double holography precise.
Probably we need to think about also ADS3 cross S3, this kind of internal direction.
The whole thing, the ADS3 times S3 times
string theory.
Yeah, people have talked about the brains in these theories.
I see. Yeah, that is really interesting.
So, but I don't know of anyone.
Maybe we can, get some information of this gravity localized on the brain.
But as you said, the gravitational theory that you talked about will then be one-dimensional, right? So there will be a one-dimensional. There's a two-dimensional CFT which will have a boundary.
Exactly.
But from the W holographic perspective,
you want a one-dimensional. Exactly. So but you might be able to construct it top-down if you have some brain construction in the D1, D5 system. You put in some additional thing, and then look at the open string modes on that boundary. And then try to see if that can capture in some ways.
You said something about how you argued it was dual theory, right?
Sorry,
you had an argument that was
effective field theory argument. Yeah.
If you have an open string construction,
maybe
then you
some kind of scattering amplitude, or maybe some computing some correlation function. Maybe get some information of gravity.
In the JT gravity context, these there is a slightly more precise understanding of these end of the world brains as random superpositions of energy eigenstates. So here, should we have something like this in mind, where we imagine some random superpositions of Cardi states or something like that?
Oh, I see. Yeah, here, but I'm talking about ADS3. So still, I mean, assuming duality CFT is not a random average.
Right.
Just single holographic CFT.
Okay.
But okay, probably may random average also give the same answer. Okay. Yeah. Okay. So yeah, there is let's work on this. I mean, bulk 2D CFT is a 3-point function. Coefficient may be interpreted as a random average. Maybe there are some analog of that. Maybe coefficient of this G function, or maybe other coefficient in front of the boundary state might be understood as some random average. Yeah, that's I think very interesting approach. Thank you very much.
Tadashi, if I can go back to your point about the null energy condition appearing
yes.
in the bulk, and I have two questions. First is okay, sorry, is it on? Okay, so I have two questions. First of all, in a general quantum theory,
yes.
The null energy condition per se can be violated, right? But not the average null energy.
Okay, yeah. Quantum corrected. Yes.
And so, what do you think is the status of not only that, but similar issue may be there more generally in terms of
yeah. So that's I think when we consider higher order correction to G function, 1 over C.
Yeah, that's true.
Yeah, then I hope that that will be also derived from this average only average one.
But I mean, from the boundary theory perspective, still the G function is defined the way it is, right? Presumably. But I'm just saying, I'm just saying the proof at least directly won't apply, but maybe it can be even violated. So that was going to be my next question. Correct. So I mean, that was going to be my next question.
But there is I mean, even quantum. If we talk about entanglement entropy and quantum correction, there is a quantum extremal surface formula. That's also kind of we are taking extremalization and minimum, and we can use this Alan Wall's argument for time-dependent setup. We can still strong subjectivity satisfy. And maybe probably that should work in that case. But I think, in other words, this null energy. But the point is, null energy condition plays a role when we rely to holographic entanglement in terms of max mean like formulation, and that part we have to be very careful.
I see. That's
but maybe that's related to some focusing, quantum focusing. So maybe but I'm not expert.
I see.
So you discussed this co-dimension 2 holography, the wedge holography. So can you make can you comment on what is the status of this? So to me that reminds of celestial holography. So is it like?
Yeah, okay, good. So we wrote a paper which tried to understand celestial holography from this wedge type holography. So because we can think about this space, flat space, in terms of some, these are, I mean, Penrose diagram flat space, but we can decompose this way, and we can have a Dojita slice and this hyperbolic space slice. And the edge, we call it like we can terminate, we have some cutoff here. I mean, we can cut off here, and also we can cut off here, and then this part looks like wedge. So it is a codimension too. So yeah, we actually indeed did such analysis, and but the result is very formal. But it's for example, if we can calculate the central charge, the 4-dimensional space-time, we have a 4-dimensional Minkowski space-time, and then this part is codimension to it's like a 2-sphere, and we can read off central charge. But central charge, for example, turns out to be I infinity. It's really non-unitary, but maybe not surprising because DS CFT also use some imaginary central charge. But it's very formal. So I don't know really what does it tell us.
Related to the second previous question, does this the proof of this G theorem works for the traversal wormhole background. If you consider traversal wormhole or like a double trace deformation, so since the average no energy condition is violated, so in this case, this doesn't work, or
I don't. Yes, it's a problem. I mean, yeah. So yeah, because if we do that, then I think you change the original. If you introduce some right, double trace deformation between A and B, then that already changes the setup. So it can be from the can be violated.
Okay, from the boundary point of view, I'm not really sure whether this really implies a violation of G theorem itself.
It's fine because you have two theory and they couple. So
okay.
It's set up with.
Thank you.
So just one more general question. Firstly, my ignorance, is there an analog of the G theorem for the 4D theories?
Yes. In 2D, so it's,
like the from the A theorem, I mean.
So. CFT, I mean, so CFT2 case, we have a one-dimensional BCFT as a boundary. CFT4 case, I think there is, so CFT is defined as three-dimensional. It's much like F-like quantity plays a role of G function. But I think probably proof is not proven.
Not proven maybe in general.
If audience know better, please.
Sorry?
If audience know much better about this one. But as far as I know, probably this guy is not proven.
Boundary F function.
Maybe,
I see. But in general, like that Cassini-Huerta proof, can it extend to the A theorem also?
A theorem is different. There is a paper by Cassini and collaborators, but they are not showing there is a function which monotonically decreasing, but they show that infrared to fixed point and IR fixed point, their inequality holds. And using quite different from strong subjectivity, some other argument. But in that sense, 4-dimensional already slightly deviates from this kind of argument. But maybe there is a chance that 3-dimensional case still this kind of argument gives proof of some kind of G theorem in 3D.
Okay.
Okay, so thank you very much, Tadashi, and we'll reconvene at 2 o'clock.